solution.
Okay, so
Let's
you want to
start.
share your screen?
Yes, let me see if I can do that here.
You're recording? I am. Okay, good. So while you're doing that, I'll introduce you. So I think everyone knows John, but if you don't, this is our friend John Kyei. How do you say your last name? Kyei?
Yes, it's
Okay,
Kyei, like C-H-E-I kind of. Kyei.
Okay. Anyway, she's going to be speaking to us about the Nevanlinna-Pick problem or interpolation problem. So, John?
Okay, can you guys see my screen?
Yep.
Yep.
Okay. All right, thank you, Nathan, and thank you all for joining. I will be giving a very basic introductory discussion on the Nevanlinna-Pick interpolation problem today. And it is very basic that no prior knowledge or any special background is necessarily required to be able to follow what I'm going to talk about. I just started this exploring this area myself quite recently, so I'm still new to the area. So any forms of contributions, comments, or like any other thing like that is sincerely welcome. All right, so I'll be starting off with Blaschke product, and then we'll work our way down to the Nevanlinna-Pick interpolation problem. But before we get into it, let me give a brief background or a brief statement of the problem. So the Nevanlinna-Pick interpolation problem is a problem that was formulated in the early 20th century by Pick. And the whole problem is that he asks a very basic question, or a very interesting question, that given a number of nodes, a number of points in the unit disk, lambda 1 to lambda n, and a number of complex numbers, omega 1 to omega n, the question is there or does there exist a holomorphic function from the unit disk to the unit disk that interpolates these points, that is, maps lambda I to omega I? And it turns out the time he was studying this problem, there was also another mathematician, Nevanlinna, who was working on the exact same thing, but I think they had not communicated amongst themselves, so they didn't know they were all working on the same problem. So 3 years after Pick published his work, Nevanlinna also came out with his own findings and his own formulation and problem solution, which happens to be almost the same thing, but Nevanlinna takes a slightly different approach from what Pick did. So Pick further asserts that the solution to this problem, or the extrema problem, and the extrema problem is that if there exists a solution, a holomorphic function that kind of does this business with a modulus of 1, such that there is no other solution of modulus less than 1 that interpolates the problem, then that kind of problem is called the extrema case, or the extrema problem. And he asserted that that extrema case has a unique solution, and in fact, that solution is a Blaschke product. So before we get into it, let's look at a few notations that are used in this presentation. So D here represents the open unit disk, and of course, D bar is the closed unit disk. T is the unit circle, and HP is the Hardy space. So for P strictly less than infinity and greater than or equal to 1, the Hardy space is just the space of analytic functions on the unit disk, such that the P norm is finite. And by P norm, I mean the mean to order P of the radial limit of the function. So F tilde here is just the radial limit. That is the limit of the function at the complex number as R goes to infinity. So as we get close and close to the boundary of the disk, what is the P, the mean of order P? And subsequently, H infinity is going to be the family of all bounded analytic functions on the disk with finite supremum norm. C caret here is going to be the extended complex plane. A of D is the disk algebra. That's the family of all analytic functions on the disk that extends continuously on the closed unit disk. Okay, so before we get into Blaschke products, let's look at a few other interesting functions. So first, let's look at automorphism. A bijective analytic function f on the disk to itself is called an automorphism. Here, we're going to denote aut D to be the family of all automorphisms on the disk. And it is actually not so hard to show that this group or this set, this class actually forms a group under function composition with the identity element f of z is equal to z. There are two special automorphisms that are of interest to us. That is, given any omega on the disk and gamma on the unit circle, we define t omega at z as omega minus z over 1 minus omega bar z. And phi gamma at z is just gamma times z. Now, if you pay attention to the phi function here, we notice that because gamma is on the unit circle, the phi function is just a rotation of the disk about the origin through an angle of the argument of gamma here. So it is indeed an analytic function from the disk to the disk, and so it is an automorphism. This one might require a little bit of work, but it's not so hard to show that for any z on the unit disk, this function has a modulus of 1, and for any z in the for any z on the unit circle, the modulo is 1, and for any z in the unit disk, by the maximum modulus principle, the modulus of this is always less than 1, and so it is an automorphism on the disk as well. And they are very special to us because it turns out all other automorphisms on the disk can be written as a combination or a composition of those two special automorphisms. So the theorem says if f is an automorphism on the unit disk, then there exists a unique omega in D and a gamma in T, such that that function can be written as a composition of phi gamma and composed with T omega. So the set of all automorphisms is nothing but the compositions of such functions. Now, for any z naught in the disk, we define a function b subscript z naught as the piecewise function we have on the right-hand side here. And this is what we call the Blaschke factor, So at z naught not equal to 0, we have what is up here. And you can see it is normalized such that this function is non-negative at the origin. So b zeta naught at 0 is equal to the norm of z naught, which is obviously greater than or equal to 0. In particular, on the unit circle, the factor has a modulus of 1, and inside the unit circle, the definition is that. And when z is equal to 0 at the origin, the definition is obviously that. And for any other point outside of the unit disk, that is the complement of the disk in the extended complex plane, the definition of the Blaschke factor is just 1 over the conjugate of the Blaschke factor, but this time at the reciprocal of the conjugate of z. So it is clear that with a little bit of work, it's verifiable that the Blaschke factor maps bijectively the disk to the disk, the unit circle to the unit circle, the complement of the unit circle in the complex plane to itself. So of course it is an automorphism. Now the modulus and arguments are interesting things to look at when it comes to the Blaschke factor, but I would like to skip all those for now and get to the point. So finite Blaschke product is the next thing that we want to look at. But first, a general Blaschke product is just a product of Blaschke factors together with this unimodular term, that is a modulus of 1. So an expression of this form such that the alpha is a real number, k is non-negative, and the sequence of points are in D, such that this condition holds is what we call the Blaschke product. So this product, together with this condition, provided the sequence of points are in the disk, alpha is real and k is positive, is called the Blaschke product. And this condition, the condition that this series is convergent, is called the Blaschke condition. Now, a finitely many of these terms is a product involving only a finitely many of these terms is what we call the finite Blaschke product. So given the sequence of points Z1 through Zn as in the unit disk and for an alpha in R, B of Z, which is the product of these finitely many Blaschke factors, together with this unimodular coefficient, is what we call the finite Blaschke product of degree n. Here, we do not require the Blaschke condition because we only have finitely many of these, and of course, the series is going to converge, guaranteed to converge. Now, these are a few verifiable properties of the Blaschke product. The first one is that it is analytic on the disk and continuous on the closed unit disk. And so it belongs to the Hardy space H infinity D, the family of analytic functions on the disk. And B here is also an inner function. An inner function is an analytic function on the unit disk to the closed unit disk such that the modulus is 1 almost everywhere on the boundary, or the modulus is 1 almost everywhere on the unit circle. And B has zeros at precisely Z1, Z2 up to Zn. So the Blaschke sequence, the sequence of Z here used in the formation of the Blaschke product is called the Blaschke sequence. Those form precisely the zeros of the Blaschke product. And it has zeros, it has poles at precisely the reciprocal of the conjugates of the elements of the Blaschke sequence. And then lastly, the equation B of Z equal to omega, where omega here is any complex number, is a polynomial of degree n. That is, if the Blaschke product is a polynomial of degree n, then this equation is a polynomial of degree n. And if it is a polynomial of degree n with complex coefficients, then by fundamental theorem of algebra, we are guaranteed to have at least one root. But as a matter of fact, this theorem tells us that we actually have n roots, exactly n roots counted according to multiplicity. So let B of Z be a finite Blaschke product of degree n. For each omega in the extended complex plane, B of Z equal to omega has exactly n solutions counted according to multiplicities. And the condition is that if omega was chosen to be in the unit disk, then the solutions belongs to the unit disk. If omega is on the unit circle, the solution is on the unit circle. And again, if omega is in the complement of the closed unit disk in the complex, extended complex plane, then so are the solutions as well. The next lemma in theorem says that if we compose a finite Blaschke product with one of the special quote unquote automorphisms on the disk, then the result is another finite Blaschke product of the same degree as the Blaschke product. We are not guaranteed yet whether this composition is commutative. So T omega composed with B is not necessarily equal to B composed with T omega, but they are all finite Blaschke products of the same degree as the starting Blaschke product. And in that case, we can say that all finite Blaschke products are closed under, what do we call it, function composition, because finite Blaschke products are analytic on the disk, and all analytic functions on the disk or automorphisms can be written as a composition of these. So basically, they are all nothing but compositions of the special automorphisms. Again, I will skip the characterization, differentiation, and approximation, and then move straight to the topic. So as I stated earlier on, the pick problem is having given this number of nodes, lambda 1 to lambda n, with n complex numbers. The question is it possible to find a holomorphic function from the disk to the disk that interpolates the data, that is, maps lambda I to omega I? Now, a lighter existence requirement, and I say a lighter existence requirement because the solution or the proof for the pick interpolation problem relied mostly on the Schwarz lemma, a version of the Schwarz lemma. So he picked the Schwarz lemma and kind of used an induction on the Schwarz lemma to get the n-dimensional solution to the n-dimensional problem. So we are using the Schwarz theorem or the Schwarz lemma as a lighter requirement or existence requirement. So the Schwarz pick theorem actually says that suppose we have lambda 1 and lambda 2, omega 1 and omega 2 as points in the disk. There exists a holomorphic function phi that maps the disk to the disk and sends lambda I to omega I, if and only if this pseudo-hyperbolic norm is such that the pseudo-hyperbolic distance, if the distance between the image point is less than or equal to the distance between the inputs, lambda 1 and lambda 2. And moreover, equality holds if the interpolation is unique, or if the equality holds, then the interpolating function is unique and is actually a Mobius transform. And by pseudo-hyperbolic norm, I mean this definition. Phi of alpha beta is given as the difference between alpha and beta divided by 1 minus alpha bar times beta. It can actually be shown that this expression satisfies all the conditions for a metric, so it is actually a metric. One other important tool that we're going to use is the kernel function, the Sego kernel in particular. So recall that HP here is the Hardy space. So here let P be equal to 2. Then if you consider the Hilbert function space H2 on a set X and the evaluation factor function E, such that it sends any element of the set lambda to f of lambda for f being in the function space. Then obviously this evaluation function is continuous and is linear functional, so we can have an inner product representation of this evaluation function by Riesz representation theorem. That means there is an element k lambda or in the function space such that f of lambda is equal to the inner product of f and k lambda for f being in the function space, or for all f in the function space. Here we call such element k lambda the reproducing kernel of the space. Now, if the space in question, in this case being H2, the reproducing kernel has a special name called the Sego kernel, and in a few seconds or a few minutes, I'll define the Sego kernel for the H2 space as in an explicit formula for the kernel. Since the kernel itself is an element of H2, it means that the kernel at lambda, so it's the reproducing kernel at lambda. So the kernel at lambda evaluated at an element Kyei can in turn also be written as an inner product. So because of this, we give it a notation that k Kyei lambda to be the kernel at lambda evaluated at Kyei to be this inner product. So let's look at the multiplication algebra. And again, these might seem like random ideas, but we're going to put all of these ideas together to prove the necessary and sufficient condition for the pick problem. So we denote here the mod H to be the set of all functions phi such that phi times f belongs to the function space H2 for all f in H2. So all such functions that has this property, we denote it as mod of H. That is the multiplication algebra. And let M phi here be the multiplication operator such that M phi acting on a function f from the Hilbert functional space is just a multiplication of phi and the function f. In that case, we know clearly that the adjoint of the multiplication operator M phi acting on k lambda is just equal to the conjugate of phi at lambda acting on k lambda, right? The adjoint of the multiplication operator. So I think it's almost clear. This was just to convince ourselves that it is actually true. Now, from that case, from that statement, we see that the norm of the multiplication operator is greater than or equal to the supremum of the multipliers over the whole set. In a bit, we will obtain the reverse inequality and actually know that these two terms are equal. Now, as I said, if you look at the function H2 functional space, the reproducing kernel for the evaluation function is the Sego kernel, and by definition is given as Ks z omega is equal to 1 over 1 minus omega bar times z. So this is a specific unique function definition for the kernel function on the H2 Hilbert space. Now, the algebra of H infinity D close, D bar, that is the set of all bounded holomorphic functions on the disk, is isometrically isomorphic to the multiplication algebra or the multiply algebra on H2. It is not so hard to show because if we consider H2 as a subset of L2 with respect to some reasonable measure and also H infinity as a subspace of L infinity with respect to that measure, then for any bounded holomorphic function on the disk, we have that the norm of the multiplication operator associated with that function is less than or equal to the norm of the multiplier. And from previous, we showed the reverse inequality that the norm of the multiplication operator is always greater than or equal to the supremum of the absolute value of the multiplier. In that case, we have that they have the same norm. And conversely, if you have a function in the multiplier algebra, since 1 is an element in the function space, because if you multiply 1 times phi, we're going to end up with an element in phi. It turns out phi here is also an element of H2. And so if it is an H2, it's going to be less than or equal to the norm of the multiply algebra. And we have that phi is an analytic function on the unit disk. So these two terms are going to be used interchangeably, the algebra of H infinity on D closure, and then the multiplier algebra on the set of functions, the Hardy space. So now let's come to the Pick theorem about the whole problem. This theorem specifies the necessary and sufficient condition for such a solution to exist. It says that there is a function phi in the closed unit ball H infinity D closure that satisfies 1. And by 1 here, I mean the problem statement, given lambda 1 through lambda n, omega 1 through omega n, does there exist, blah, blah, blah. So there is such a function if and only if the Pick matrix associated with that problem is positive semi-definite. Now the Pick matrix is this definition, this matrix definition involving the data in the problem. Lambda I and omega i's here are all elements or are numbers or are points from the problem statement itself. Moreover, the interpolating function phi is unique if and only if the rank of the Pick matrix is strictly less than the dimension of the problem. So if the rank of the Pick matrix is m, which is strictly less than n, here we have lambda 1 through lambda capital N. So if this happens, then the interpolating function is unique. And if we have a unique case, then the solution is a finite Blaschke product with degree which is equal to the rank of the Pick matrix. So as I said earlier on, the solution process relied on the Schwarz-Pick theorem. And the Schwarz-Pick theorem says that given lambda 1, lambda 2, omega 1, omega 2, such a solution exists if and only if this condition is true. Now we're going to use this condition, use the fact that the matrix is positive semi-definite and this identity to show that if we had a two-dimensional problem, it indeed verifies or it indeed confirms that the Schwarz-Pick condition is true, or it confirms the Schwarz-Pick condition. So we're going to use this identity it requires quite just a few steps to verify that this is equal to that. So now, because we have just a two-dimensional problem, so here we have lambda 1, lambda 2, and omega 1, omega 2, the Pick matrix associated with this data is what is shown here. Now, the diagonal elements of this matrix are all positive. Remember, lambda and omegas are all in the unit disk, so the diagonal elements are all positive. So for this matrix to be positive semi-definite, we require that the determinant of the matrix be non-negative. So we multiply out this times this minus that times that, And we notice that the determinant is non-negative if and only if this condition holds. So the determinant is non-negative if and only if this condition holds. But this condition is closely related to the identity that we started with, just that this one is missing. So this is just equal to 1 minus the the left-hand side. And the left-hand side, as we noted, is actually the pseudo-hyperbolic distance that we were talking about. So we end up with this inequality, which is in actual sense is just the Schwarz-Pick condition. I mean, we can take out the squared and we get back to where we started. So it's indeed that if the matrix associated with the Pick problem is positive semi-definite, and we have an interpolating function, then the condition, the Schwarz-Pick condition, is satisfied. Now there is an operator theory flavor to this problem. There's a little bit of a connection because as we started talking about the multiplication operator and all that. But one important aspect of operator theory that we're going to be using is that the Sego kernels are eigenfunctions for the adjoint of the multiplication operator m phi. Because by definition, we said that the adjoint operator acts on the Sego kernel by this definition. And this is just the eigenvalue eigenvector setup. So the Sego kernels are eigenvectors of the adjoint of the multiplication operator. And so suppose there exists an interpolating function, then for each I, this is what happens. The multiplication operator associated with the phi function acting on the kernel element, or now the eigen space element, is going to give us the conjugate of phi acting on the kernel element, which in actual sense is going to be the conjugate of omega I acting on the kernel element. That is because here we are supposing phi here interpolates the data. So that means that phi of lambda I is equal to omega I. So for any phi that satisfies the problem, the action of the adjoint of the multiplication operator on the space that is spanned by the, what do we call it? The kernel functions. And here I mean k lambda I is completely determined. So because of this statement. And in this case, Pick's theorem can be interpreted as such. If the norm of the adjoint operator restricted to the subspace of the function space such that the norm is always less than or equal to 1, then there is some interpolating function phi such that the norm of the multiplication operator itself is less than 1 on the whole of the function space. And if this happens, then we have a confirmation, or that has an affirmative answer to the Pick problem. So this we put together and call the Pick property. What does the Pick property say? The fact that the action of the adjoint operator on the subspace spanned by the kernel function can be extended to the whole space without increasing the norm. That is a special property of the Hardy space. And as we just noted, if we have this condition, there's a guarantee of a solution, which we're going to prove in no time. So a more general question to ask at this point, because we know that the family of all bounded linear, the family of all bounded holomorphic functions on the disk is actually isomorphic to the multiplier algebra on L2, we can reformulate the problem as given an H2 Hilbert function space on X. If we let lambda 1 through lambda n be points in X and omega 1 through omega n be complex numbers, then when does there exist a multiplier phi of H2 of norm at most 1 that interpolates the data? So the Pick problem can be reformulated or restated in this, this way. So now we go to a necessary condition. A necessary condition to solve the Pick problem with a multiplier phi belonging to the multiplication algebra on H2 or of H2 of norm at most 1 is that the matrix associated with the problem be semi-definite. And this sounds like we've said it before. That is because now here we are replacing the this particular term in the Pick matrix with the kernel functions. You notice that the the Pick matrix is a special case of equation 8 here if the kernel function is the Sego kernel. That is by the definition that we had. So in this case, we see if we can prove this necessary condition that there is such a multiplication function in the multiplier algebra of norm at most 1 that interpolates the data if and only if the Pick function is positive semi-definite. So let's see if we can prove the necessary part of the condition. So suppose we have such a function that satisfies this, that interpolates our data. Then the multiplication operator associated with that phi is a contraction. It's a contraction because we said the norm is less than or equal to 1. So from operator theory, since it's a contraction, we have this. For every contraction map, the difference between the identity and the composition of the map and the its adjoint is always positive or non-negative. So for any vector v in the space, we know that this is going to be greater than or equal to 0. So in particular, because this condition holds for the entire space, it also holds for the subspace that is spanned by the kernel elements. So let's pick a V that is in the subspace spanned by the eigenvectors of the adjoint multiplication operator. So V can be written as a linear combination of the kernel functions. In that case, applying this to here, or substituting V for in the previous expression, and recalling the idea that the action of the adjoint multiplication operator on the kernel is given as such, and also from the hypothesis that phi is the solution, or phi is the function that interpolates the data, putting all these three things together, we arrive at this expression. So we have that because the AIs, I think there should be a bar here, because the AIs are just arbitrary constants, it means that the Pick matrix, which is basically by definition, is going to be positive semi-definite. So if the solution exists, then the Pick matrix associated with the problem is positive semi-definite. Now that is only the necessary condition, but for sufficiency condition, we use a special property of the Sego kernel. So the Sego kernel has the scalar pick property. And here I'm saying scalar pick property because the pick interpolation problem has a matrix value version. That is, you can interpolate matrices as well. So here I'm just sticking to interpolating constants. So the proof to this particular theorem is quite, I don't know, all versions that I've seen so far spans a number of pages. So what I did is I just summarized the proof here so we can get a feel of what the bigger picture. So suppose lambda 1 through lambda n are the given points and omega 1 through omega n are the complex numbers, such that the Pick matrix is positive semi-definite. Now we want to show that there is a function phi in the multiplier algebra of H2, or in the set of in the Hardy space H infinity that interpolates the data. Now let's consider the subspace M of H2 that is spanned by the kernel functions. So M is equal to the span of the kernel elements. And let's define the operator R on M by this. So R acting on the kernel element K lambda I is going to be omega I K lambda I, where I runs from 1 through n. So notice that R is a contraction because R is a contraction because the matrix is positive semi-definite. And we can verify it by this expression. Remember, I said if from operator theory, if an operator is a contraction, then this term we have here is going to be positive. And as we can verify, this is the single, so this is going to be greater than or equal to 0. So it is clear that the operator defined on the subspace spanned by the kernel elements is a contraction. Now let's keep that idea on the side for a minute. And let's consider the unilateral shift operator on the H2 space. So the unilateral shift operator acts like, or is a multiplication operator that just multiplies the function by z. So in that case, it is easy to show that the adjoint of the unilateral shift operator is just the conjugate of lambda here times the function. So this is behaving exactly like the M phi, what do we call it? Operator. So if that happens, then because the adjoint of the multiplication operator M phi star here is acting on an invariant subspace which is spanned by the kernel elements, and this guy is exactly the same thing as such a multiplication operator. It means M, which is the subspace spanned by the Sego kernels, is invariant under S star. And also S commutes with R, just with a little effort, this one can be shown that the adjoint of the unilateral shift operator in this case commutes with the operator we just defined. So this lemma says that if an operator or an operator that commutes with a restriction of S star on an invariant subspace has an extension to an operator of the same norm that commutes with the adjoint of S on the whole space. So since R commutes with S star on an invariant subspace M, it means that R is just the restriction of a bigger operator or of an operator that acts on the whole space H2 that commutes with S star. So R here is just the restriction of G onto M such that G acts on the whole of H2 and commutes with the adjoint of the unilateral shift operator. But what kind of operators act like that? So that means that G would have to be the adjoint of another operator that commutes with S. If G commutes with the adjoint of S on the whole of H, then G is the adjoint of an operator that commutes with S. So G is equal to some H such that G equal to some the adjoint of H such that H commutes with S. But any operator that commutes with S is a multiplication operator. So in that case, R is nothing but a multiplication operator, the adjoint of a multiplication operator that is restricted to the subspace M. So R is the adjoint of a multiplication operator restricted to the subspace M for some phi in the Hardy space. So in that case, by definition, we just said that M star phi, which is the adjoint operator, acts on the kernel elements as such. But M star phi is now R. So this is equal to R acting on the kernel element. But R by definition is equal to omega bar I acting on the kernel element. So that means that phi bar at lambda I is equal to omega I bar. So that means that the conjugate of phi at lambda I is equal to the conjugate of omega I. And for that matter, we say phi interpolates the data. That would mean that phi of lambda I equal to omega I. So now that is the sufficiency condition. Now we turn our attention to the extrema case. And the extrema case is when we have a function phi that interpolates the data with modulus 1 or with norm 1, such that there is no other function that interpolates the data with norm less than 1. If that happens, Pick proposes or Pick asserts that the solution to such a problem is unique and is in fact a Blaschke product. Because of time, I will not be able to go through the whole proof, but let's look at some bullet points of the proof. So suppose we have the interpolation problem, lambda 1 through lambda n, omega 1 through omega n, with a Pick matrix which is positive semi-definite. And we let V be any non-zero vector in the null space of the Pick matrix. Then for any lambda in the complement of the nodes in the disk, so for any lambda in the disk such that it is not equal to any of the original data, the original nodes given in the disk, there's at least one omega such that the new Pick matrix, which is n by 1 by n by 1, is still positive definite. And that new matrix is just more or less like an augmentation of the new factor with the original Pick matrix. And applying this to the vector, which is now n plus 1 by 1. That is, you take the original vector V, which is in the null space of the Pick matrix, and then you add one more component. So is the, I don't know whether I can call this the augmentation, but the original matrix with one new component. Then if you apply this new Pick matrix to this one, noting that the original V was in the null space of the original Pick matrix, we end up solving for W as such. Sorry, omega as such. So this is an explicit expression representing omega. And we see from this expression that it has these properties. Both the numerator and the denominator are linear combinations of the Sego kernel, where Vi here is just the ith component of the vector in the null space of the Pick matrix. So both the top and the down are linear combinations of the Sego kernel, and they are linearly independent. They are meromorphic on the complex plane with at most n zeros. So therefore, they are undefined at most at the nodes, the original nodes of the Pick problem. So since lambda was chosen to be in the complement of that set, the singularities are removable. So if we do that, the definition or the formula for omega here is nothing but a bounded analytic function on the disk. And since it is a formula for W, it is unique. And Pick says that this is the unique solution to the extrema Pick problem. And it's all summarized in this theory. So with the given notation, any extrema Pick problem for the Hardy space H infinity D has a unique solution that is given by this formula, which is also a Blaschke product of degree n. So it is easy to verify that the modulus of phi lambda is equal to 1, and also phi lambda I is equal to omega I. So as I said earlier on, these two people were working on the problem at the same time, or within a close time frame, without knowing, of course. So Nevanlinna on his own also solved a problem with a very unique characterization. And his solution, or his characterization of a solution to the Pick problem, is that he asserted that if there is more than one solution to the pick problem, if the pick problem has a non-unique solution, then the family of all solutions can be parametrized or can be written in a special way. If the pick problem lambda I equal to omega I, such that phi of lambda I equal to omega I, such that the norm of phi is less than or equal to 1, has more than one solution, then the set of all solutions is of the form f equal to p phi plus q over r phi plus s, where these parameters are related by this formula, ps minus qr equal to b, where b here is a finite Blaschke product with zeros at the given nodes. So these lambda i's are the nodes of the original problem. So if there is more than one solution, then all the solutions can be characterized or parameterized as such that these parameters are related by this. And he also asserted that all the solutions lie in an Euclidean disk of a certain radius and a certain with a center. So the set of all solutions is a Euclidean disk of a center C of Z and radius R of Z that is given by this formula. And R is given by this. So all the solutions is an Euclidean disk with a center this and what do we call it? A radius that. There are other closely related formulations of this problem, like the characterizations formulation or the characterizations problem, which instead of picking endpoints and n complex numbers and try to interpolate them, he says, what if I pick a holomorphic function on the disk and I take the first n plus 1 coefficients of its Taylor expansion? Is there or are there other complex analytic functions or holomorphic functions on the disk? So about the point 0, are there other holomorphic functions on the disk that has these coefficients as their first n plus 1 Taylor coefficients? And it's also an interesting problem that I'm looking into at the moment. But for now, this is all that I have for you. Thank you very much. And if you have any questions, please let me know.
I still don't know how to make that not awkward, but good talk. So does anyone have any questions? I have a few, but does anyone else have questions first?
Yeah, I have a question.
Okay.
Hello, John.
Yeah, sure.
Yeah.
Ray, I'm here.
Hey, how's it going, John?
Cool. How are you?
Pretty good. Just trying to understand what you're saying for the main statement of the pick problem, because I feel like there should be some condition on the function, because it seems like you're saying that the problem is whether or not there exists an interpolating polynomial, just period.
Yes.
But isn't that always the case?
It's not a polynomial.
It's an interpolating holomorphic function.
But you can just say there exists an interpolating polynomial and then be done, right?
Because you can approximate the holomorphic. Wait a minute.
It's the condition below that's important, right? The disk to the disk. Not all polynomials do that.
So this
okay.
This function or this holomorphic function must have a norm
of
most 1.
Mm-hmm. Okay.
Okay. Any other questions? If not, then I have 1 or 2.
Okay.
Sure. I'm here.
Maybe I can ask one question.
Okay, Fidel.
So where did you apply the Schwarz lemma in the proof?
The Schwarz lemma?
Yeah, where did you apply it? the Schwarz lemma.
So in this particular proof, there are variant proofs, by the way. In this particular proof, I only use the Schwarz lemma to verify that if I have an interpolation function from the disk to the disk for the two-dimensional problem, then indeed the Pick interpolation, the Pick matrix associated with that problem is actually positive semi-definite. So let's say I use the Schwarz-Pick theorem here as just an example, but there are other proofs that kind of combines both the necessary and sufficient condition differently, like from what I did here, where they just use induction. So they start from the two-dimensional problem and just induct up to the n-dimensional problem. Okay.
Okay, Nelson, you can ask.
Okay, so one is a very vague question. I just wanted to know if you had any answers to it. So, do you know Schwarz, or not Schwarz, Nevanlina or Pick's original motivation for, well, they're interested in
motivation for the problem?
Yeah, like what were they interested in doing? Was there something specific, or was it just like they had an interpolation problem they wanted to solve?
So by far, I haven't come across any documentation of what they were actually doing that led to this problem. But I know he was around the age of 21, so a lot of things come in mind around that age. So he could have just thought of it out of nowhere. I don't know.
Okay. And then question 2. So could you go down to, I think it was like second to last or third to last slide?
Okay.
Sorry to make you scroll all the way back.
Let's go to 30, maybe. Am I close?
It was about the form of the, so Nevanlinna's parametrization.
Oh, the formula.
Yeah.
Okay.
So that was interesting looking, I think. But I had a question about exactly what it's saying. So keep going, okay. I think. It was like, where was it?
So he takes the matrix.
Next slide 38 maybe. So he had this, it looked like Mobius kind of transformation, only the coefficients were all taken to be, well, I guess that was part of the question. So I didn't fully understand exactly what.
Okay, so here, bear in mind, here we are talking about the extrema case. So here the assumption is that the Pick matrix is already positive semi-definite because we have an interpolating function that has a modulus of 1, right? A norm of 1. So now he takes lambda to be any point outside of the given data points. And he takes a vector, a non-zero vector in the null space of the Pick matrix, which is already positive semi-definite. And then he augments this to get a new Pick matrix. He augments the new lambda and new omega to get a new Pick matrix. And somehow uses the idea that the vector is in the null space, and then phi is an interpolating function, and also the matrix, the original matrix, is positive semi-definite. So multiplying that matrix with a new vector, which is formed by just adding one component or one whatever it is, a c to the original the null space element, is able to deduce that omega has this formula. And it turns out this omega formula also works for all the previous data points, starting from lambda 1 to lambda I.
Sure, okay. So maybe it's 2 more slides down, keep going.
Okay.
So it applies to...
oh, you mean the Nevanlina problem? The Nevanlina formulation?
So keep going, keep going. It's like slide, this, that, yeah.
Oh, the center and the radius of the Euclidean, they square all the solutions.
Yeah, so where did we get that? I mean, that seems, do you have a reference? That just looks interesting to me, I guess. It's very mysterious.
This guy has a paper, what's his name, Sasson? That is why I got this. And honestly, I'm a little bit limited as in by how far I can either justify or verify or, defend this particular formula. But the claim is that they all fall within some disk. an Euclidean disk, and the radius of the disk is calculated by the modulus of the Blaschke product, which in this case is the same as this expression, the difference between these two parameters, like product and parameters, divided by, I know you're going to get a constant somewhere, but the dimensionality is kind of something I need to read more on.
Yeah. Okay. Well, it's an interesting formula nonetheless. I think maybe we'll talk later about how, or just more about it. So any more questions from anyone else? If not, then let's thank our speaker one more time. And well, I'll stop recording and we can just talk after this.
Give you the opportunity.